So first I would like to thank the organization for giving us the opportunity to present this work. So this is work in collaboration with Gesa Jenscha. So he works at the Slovak University of Technology and I work at Johannes Kepler University. So this work is still work in progress, so the whole concept of a semi-Cartesian category relation is not definite yet. But yeah, first it might be good to talk about our motivation. We're interested in the quantization of mathematical structures in the sense of finding non-commutative generalizations of those structures. And we are interested in particular in applications to quantum physics to describe quantum phenomena. And the way we want to do this is we look at a category of non-commutative structures and we want to internalize the structures we want to quantize in this category. And some example of what we found is the notion of a quantum CPO, which is a non-commutative generalization of ordinary CPOs, and ordinary CPOs are used to describe computation, and in the same way quantum CPOs can be used to model quantum computation. Now, there are some connections with falsification, but the most important thing is this category in which we internalize behaves very much like the category of sets and binary relations. So we are looking at some categorical structure which describes such a category. Now, and there are in the past some categories which behave like relations, like allegories or like categories of relations. And unfortunately, that doesn't apply to our category, so we are looking to find something different. Now, and we are inspired by the categorical axiomatizations of various dagger categories as in the previous talk. Now, first, in order to say something about what are non-commutative structures, I want to talk about the notion of operator algebra, which is an algebra of continuous linear operators on some Hilbert space. Now, the standard example is the algebra of all continuous linear operators, and it might look perhaps a bit exotic, but in the finite dimensional case it's very familiar. It's just matrix algebra. Now, matrix algebras can be used to describe qubits, so D-level quantum systems. If D is 2, then you get the notion of a qubit. And generally, operator algebras can be used to describe quantum systems. The nice thing is that also classical systems can be described by operator algebras, which in this case are commutative. And it's very nice because then we can describe quantum and classical in the same mathematical framework. Now, and this is based on another example of operator algebra, namely if you have a compact Hausdorff space X and you look at all continuous complex valued functions on this, then you get a so-called commutative unital C-star algebra. And it turns out that all commutative unital C-star algebras are of this form, and we in fact have a duality between compact Hausdorff spaces and commutative unital C-star algebras. And because of this, often arbitrary unital C-star algebras are regarded as non-commutative compact Hausdorff spaces. And often it's even the case that theorems on compact Hausdorff spaces generalize to unital C-star algebras. Now, and this whole observation is one of the foundations of non-commutative mathematics, in which we try to describe quantum phenomena in terms of operator algebras. And an important step here is mathematical quantization, where we generalize mathematical structures to this non-commutative operator algebraic setting. And so an example is what we already mentioned, non-commutative compact Hausdorff spaces. And in general, we have a bit like this picture. We have some quantum system, we want to model it mathematically. So what do? Often a quantum system has a classical counterpart, and then we take the mathematical description of this classical counterpart, we quantize it, and that gives them a description of the quantum phenomena. And often this yields very natural models in the sense that it's close to physics. And the most spectacular example is probably the non-commutative standard model. So the standard model of physics describes 3 of the 4 fundamental forces. And Alan Kohn found a non-commutative version of this. It turns out that this also describes the 4th force, namely gravity. Now, there's a whole non-commutative dictionary of various structures which have a non-commutative generalization. I want to focus especially on sets because many mathematical structures are described in terms of sets. So, a non-commutative set, we identify that with possibly infinite sums of matrix algebras. And such algebras are also called hereditarily atomic von Neumann algebra. As we have seen, a matrix algebra is determined by a finite dimensional Hilbert space. It follows that such an algebra is determined by sets of infinite dimensional Hilbert spaces, and such a set is also called the quantum set. You can work either in an operator algebraic picture or in a dual picture of these Hilbert spaces, it's all equivalent. And I prefer to work in the latter picture, but in any case I will just refer to both the algebras and these sets just as quantum sets. Now, functions are generalized in this picture by the usual concept of morphism of von Neumann algebras, namely normal unital star homomorphisms. And you can now form a category of hereditary atomic von Neumann algebras, the opposite of it, equipped with these morphisms, and then you get non-commutative generalization of the category of sets. Now, this category behaves very much like a topos. So, even a grothendieck topos, because it's complete and co-complete. It is symmetric monodal closed. It's not Cartesian, but it's what we call semi-Cartesian, which means that the monodal unit is the terminal object. And then you get projections, and it turns out that in QZ we have that if you have such a diagram, you have at most one morphism which makes the diagram commute. So existence is not assured, but uniqueness is. And there is also something which very much looks like a sub-object classifier. But the only difference is that there is only a unique classical morphism, so that's some type of morphism, which you can define completely in terms of the categorical structure. But you don't have here a unique morphism, you only have a unique classical morphism. So it's not quite a sub-object classifier, but it works a bit in a similar way. Now, many mathematical structures are not just based on sets and functions, but also on relations. So, for instance, an order relation is not a function. So we want to have a non-commutative version of a relation, a binary relation. And so the question is, what is that? And normally in category theory you can define internal relations as sub-objects of the products of the source and target objects. And for several categories that yields a nice calculus of relations. So for instance for topoi, or for regular categories, more general. And in these cases also the associated categories of relations have a nice axiomatization. So for instance for topoi you get power allegories, and for regular categories bicategories of relations. But the problem here is that QZ, the tensor product, is not Cartesian but it's semi-Cartesian, and is in effect the sub-objects of their product of objects is don't yield an interesting calculus of relations, or at least not relevant to quantum physics. So a solution is by taking the notion of a non-commutative relation as a primary notion. And the right primary notion was found by Kuperberg and Weaver, who quantized metric spaces, and they based this quantization on a notion called quantum relations, which are certain bimodules between von Neumann algebras. And these are the proper non-commutative generalization of ordinary relations. Now you can form the category of von Neumann algebras with these quantum relations, then you get the dagger quantiloid, so you get the dagger. Quantiloid means that it's enriched over the category of complete lattices and supreme and preserving morphisms. And if we restrict to this hereditarily atomic von Neumann algebra, so to the quantum sets, then we actually get the dagger compact quantiloid. So that's very nice. And the category of relations, of ordinary relations between ordinary sets, is also a dagger compact quantiloid. Now, this is proven by André Cornell. Now, in a dagger quantiloid, we can define an internal map, and it turns out, so if R here is the category of relations, then you get back the ordinary notion of a function, and it turns out that the maps in QREL, this category QREL, give you exactly this category of quantum sets and quantum functions. However, as we said, QREL is so QREL is neither an allegory nor a bicategory of relations, and that is because of QZ has a Semicartesian product. Some other things, so there is some notion of a double categorical notion in which two classes of morphisms are combined. One class is more relation-like and the other class is more function-like, and it's united in one framework, and the framework is called framed bicategory. And it turns out that QZ and QREL form such a framed bicategory. But yeah, this is subject for further research. Now, we define now the process of discrete quantization as the process of internalizing structures in QREL. And some examples, so in a dagger quantiloid we can generalize the notions of reflexive relations, transitive, symmetric and antisymmetric. And now we can define, for instance, a pre-order, a quantum pre-order on a quantum set to be a quantum relation which is reflexive and transitive in this form. So if your dagger quantiloid is the usual category of relations, then you get the usual notions of reflexivity and transitivity, etc. Now there are some issues, because quantization is not an algorithmic process. That's with a lot of processes which end on ation, like oidification, categorification, and internalization. So it's often that the inverse processes are algorithmic, but not the processes themselves. And as an effect, there are bifurcations. So it happens regularly that you have some structure you want to quantize, and then you can find several inequivalent quantizations of the same structure. So how to deal with that? So yeah, we have some guidelines for that. So given a structure you want to quantize, you consider its associated category, then you quantize it, and you form a category QC of the quantized structures. Now, and then the quantization makes sense if it turns out that QC has similar categorical properties as C. The only difference is if C is Cartesian, then QC is generally semi-Cartesian. So that's due to the quantum character of QREL. And furthermore, often we would like QC to be enriched over C. Now, an example is the category of pre-ordered sets and monotone maps is complete, co-complete, and Cartesian closed. And we can form a category of pre-ordered quantum sets, and that is also complete and co-complete, and it's symmetric monodal closed in this case. Now, often it turns out that theorems on C, structures in C, generalize to theorems on structures in QC. But you have to work for it, and the strategies we use are often based on Hilbert space techniques, because the underlying objects are based on Hilbert spaces. But what I prefer is trying to translate the classical proofs in terms of the structure of REL and then lifting that to QREL. Now, there's also something similar going on in the world of falsification, where you consider unital commutative quantile phi, and then you can consider the category of phi-valued binary relations. So this turns out also to be a Dagger compact quantiloid, and the question is falsification then the same as internalizing in phi-rel? In any case, the unifying setting is that of Dagger compact quantiloids. Now, there are some results we found. So we have notion of quantum version of the power set monads. We have also a notion of quantum lower set monads. We can define quantum sublattices as algebras for these monads. So with sublattice, I mean a complete lattice, but then with morphisms which are supremum preserving. Now, it turns out that several theorems carry over to quantum sublattices, and the proofs are completely based on this categorical structure, so that's nice. Now, the existence of these monads on the previous slide follows from the following abstract theorem, where you have a set-like theorem, a set-like category which is monologue closed. You have a compact category R, you have an embedding of S in R, and then there's some technical condition. And if this holds, then it turns out that J has a right adjoint, and then the composite of this adjunction yields these monads. So, for example, if you take S is set and R is REL, then you get the power set monads, and something similar holds in the quantum case. And we have here lower set monad, which is obtained by taking S pre-ordered sets, and for R the category of pre-ordered sets and monotone relations. I will come to that in the next slides, and there is also a quantum version of that. So what's a monotone relation? It's basically a binary relation between pre-ordered sets, which is upwards closed in one variable and downwards closed in the other. And in categorical language, if we regard pre-ordered sets as categories, then a monotone function is the same as a functor, and a monotone relation is the same as a profunctor. Now, the category of pre-ordered sets and monotone relations turns out to be compact closed, and we showed that also the category of internal pre-ordered sets and monotone relations is compact closed, and as a result, this category of quantum monotone relations is also compact closed. Now, we want to understand discrete quantization better, and for that it's important to understand the structure of QREL better. And also, we want to get rid of any remaining Hilbert space arguments and just do things purely categorically. Now, QREL is not an allegory, it's also not a bicategory of relations, so we want a new notion of category of relations, and we try to get that via Dagger structures. And eventually we hope also to find a categorical characterization of QREL in the same spirit as the previous talk. So there are some other categories which already have been characterized. So we saw this in the previous, no, we saw this one in the previous talk, but then with contractions. For this talk, the work of André Cornell is very important, because we were very much inspired by his work here, and also the work of Chris on Dagger kernels was very important. So our proposed preliminary definition of Semicartesian category of relations is a category which is Dagger compact. It has precisely two scalars, it has all Dagger byproducts, it has Dagger kernels, and for any effects, so an effect is a morphism of codomain with a tensor unit. So there's precisely one effect with zero kernel, and then you can prove certain facts, and the first was already done by André Cournel. So it follows R's quantiloids, and the first four, all the axioms imply that the Hom sets are actually complete modular lattices, and you can also derive that the internal maps form a semi-Cartesian category. Okay, now some proof sketch. So the dagger byproducts give you sums of parallel morphisms, and the scalar condition gives that the Hom sets become idempotent commutative monoids, and those if you have such a monoid, then it turns out that the sum is actually a supremum. And the dagger kernels always form a orthomodular poset. That's work of Chris. And also you can write any effects in this form. And for some effects with zero kernel, with the effect condition that there's only a unique zero kernel here, effect with zero kernel, that gives us order isomorphism between the dagger kernels of objects and this Hom set. And then compact closure gives us an order isomorphism here. And so since we know that this is orthomodular and this is a complete lattice, then it follows that both are complete orthomodular lattices. And, this inherits everything. Now, in allegories we have a notion of power objects, and that's if the embedding of the maps of R into R has a right adjoint. Well, we lift this just to our dagger compact quantiloids. And for example, QREL has the power set monad, which provides the power objects. For QREL, it's the quantum power set monad. Now, and then you can prove that under all these conditions, then you have power objects for a dagger compact category. And so the first is that the maps is symmetric monodal closed. The second condition that corresponds to that weird condition in the abstract theorem on adjoints. So yeah, this might be another axiom we could impose for semi-Cartesian categories of relations, because this would ensure that B holds. And it's also the question that if we do the converse, if we assume that we have power objects, do we get then that maps of R is monodal closed? I think this is true. I've been working on this, inspired by the situation between allegories and topoi. But yeah, I still have to work on finding whether this is indeed the case also for this semi-Cartesian setting. Now, conclusion. So we found we find a quantization method by internalizing in some nice category, and we try to find axioms for QREL, which generalize both REL and QREL, and axioms imply some nice properties, and we have almost that monodal closure of the internal maps imply power objects, and from all these things we can define quantum sublattices, and we can also prove theorems from abstract structures. And with this I would like to finish, and thank you for your attention.
So maybe two quickly, if I may. So the first is you had this property that the maps from x1 tensor x2 into x1 and x2 were jointly heavy, right?
Not in this setting.
I thought you said that. You said something like that.
I think this talk I haven't used that, but it's not true in any case in QREL. I thought at some point it was true. I thought it was true, but it turned out to be wrong.
Okay, all right. So then the question, so you have this carrier of quantum sets. Now, you could do something a bit more you kind of remove the analysis from this, right? So rather than objects being certain similar, you could replace them with certain topological groupoids, and then look at groupoid correspondences between them. You sort of get a non-linear version that would still have some non-commutativity in it. So I wonder if that might be sort of interesting. Then you can separate out the bit which is sort of, there's some analysis, there's some linear approach on the whole, from the bit which is kind of purely non-commutative.
That might be an interesting way. I have not thought of that, to be honest. Thank you.
I think Clémence has the last question because then the question will have.
Okay, the construction of André Joyal, Dominique and which embeds well into a compact closed category. Do you know this?
No. No.
It would be interesting to have a similar construction for your QL.
Yes, yes. Well, yeah, in fact, we have something happens here, I think. Oh, you said that QRL would embed in?
No. Is there a similar analogous construction of QRL into a compact closed category or something similar? Because for RL, this is a very functorial construction.
Yeah, but QRL itself is already compact.
Closed.
Yeah, it's even Dagger compact. So, but yeah.
So,